Okay, we seem to be all set. I hope you had a good weekend. We have 2 weeks of lectures to go, and then that's it. Um, so last time I started chapter 10, graph theory, gave you some basic definitions. I will continue today with more definitions. I don't have many results to show you up to this point. It'll come. I don't know if you started the webworks or not. If you did not, that's fine because I still have to cover a lot of stuff. But if you have questions, let me know. So we've reached section 10.3, and we're going to talk about so-called graph representations. I sh- I sh- I should edit this, but in fact, it's really it's. I have to do this, but it's really sort of silly. Graph representations, as done in the book and as the ministry wants us to do it, is just anyway. Um, Okay, so we've seen the notion of graph and digraph, and we're going to see a few different ways to represent these structures. Um, and we will also talk about the notion of isomorphism, um, and as the name says, iso as in equal and morphism as in shape, same shape. So graphs are isomorphic. It's if you're looking basically at the same graph, but they've been presented in different ways. So we'll talk about that too. I will also cover, I think, most of section 10.4 today. We'll see how it goes. Okay. So some ways to represent graphs. Okay. So let's say we have a graph G as pictured on the slide here. Um, I can I can represent this graph in many ways. So the standard way would be to give you the set of edges. So in this case, we have the edges A, B, A, C, A, E, E, C, E, D, D, C. This is the standard way of representing a graph, where you just give all the possible edges. Mm. Now, if you have isolated vertices, then you wouldn't know just by the list of edges if they were there or not. So you'd have to be given the set of vertices also. This is not a huge deal. Um, an adjacency list. This is really just I'm just repeating what's in the book, but really just this is silly. Um, so what's an adjacency list? It's exactly what you see in this example here. So you list all the vertices of the graph here. It's A, B, C, D, E. And next to each of these vertices, you write all the vertices to which the given vertex is adjacent. So for example, here A is adjacent to B, C, and E. So you write B, C, and E here. Okay, so this is an adjacency list. It's sort of silly, so I wouldn't worry too much about that. We can do the same for a digraph. Recall that a digraph is a directed graph. So now the orientation of edges makes a difference. So you can have an adjacency list where you will give the initial vertex and then list all the terminal vertices for that particular initial vertex. So here, for example, V1, there's an edge going from V1 to V1, and there's an edge going from V1 to V2. So these are the terminal vertices with initial vertex V1, right? V4 is what we call a sink. I don't know if we'll need that, but it has no edge going out of it. So terminal vertices corresponding to an initial vertex V4, there's none. It's empty. Okay, so obviously you see that if you're given a table like this, then you have all the information that you require for your digraph, right? Okay. This is a slightly more subtle representation of a graph, and it turns out that it has a lot of applications, which we're not going to see. We're going to see one. We're going to see one in 10.4, a slightly non-trivial fact about the adjacency matrix of a graph. So you're given a graph and you choose an ordering of the vertices. This is important. You have to choose some definite ordering of the vertices here. Let's call them V1 right up to Vn. So once you've chosen this ordering, what you call the adjacency matrix of G. So if you have n vertices, so it's an n by n matrix, okay, where the entry at row I in column J, let's say Aij, is 1 if Vi and Vj are adjacent, and it is 0 otherwise. So it is a 0-1 matrix. There's only zeros and ones, and ones indicate that the corresponding vertices, row and column, are adjacent. And if it's a 0, they're not adjacent. Okay, so here is an example of this. So it's not as easy to read for a human, right? So you need to analyze a little bit more. But the fact that it's a matrix and we have all sorts of tools to play with matrices will allow us to do many, many interesting things, few of which we're going to see here because it's way too advanced. So here's a same example. I have my graph with vertices A, B, C, D, E. I choose the ordering A, B, C, D, E. I'm going to get a different matrix potentially if I order the vertices differently. You have to be careful with this. Okay, so here we choose that specific ordering A, B, C, D, E. So the adjacency matrix now is the following. So think of the rows as being indexed by A, B, C, D, E, and the columns A, B, C, D, E, like that. So let's take the one which is here, for example. So this means that C and D are adjacent, which they are, right? So this one here corresponds to, no. So this one here corresponds to this adjacency here between C and D. Does everybody sees what I'm doing? Makes sense?
Yeah. Can you just go back to the last slide for like 10 seconds?
Yep.
Right. That's it. Thank you.
Okay. All right. So so you see again that if you're given the adjacency matrix, okay, good question. Will it always be symmetric? Just wait until the next slide, and you'll have your answer and more. So we have all the information that we need about the graph if we have the adjacency matrix, right? So, but again, you have to fix an ordering. If you have the graph, you want to create the matrix, you have to choose an ordering the vertices, which doesn't seem like a big deal in the sense that, I mean, yeah, that's one of the answers, yes. But it plays an important role. This choosing of the ordering is important in a sense. We'll see just in just a sec. Digraphs. Okay, so we can create the same kind of matrix for a digraph where you're going to put a 1 if there's an arc from Vi to Vj. Now, as the discussion in the chat has been illustrating, yes, the matrix you're going to get is not going to be symmetric in that case because arcs don't go both ways necessarily. So here, if I choose the ordering V1, V2, V3, V4, this is the adjacency matrix that we're going to obtain for that particular digraph, right? So V1 to V1, V1 to V2, no arc from V1 to V3, and no arc from V1 to V4. and so on. Okay. And again, if you're given the graph, you can get the digraph, you get the matrix, and you have the matrix, you get back the digraph, same information. Okay. So yeah, so this is where I was going. In if you've done a bit of linear algebra, then you know about matrices and all sorts of stuff related to them. So some natural properties of matrices are reflected in the digraphs or graphs and vice versa. For example, what's a loop, right? A loop is an edge going from a vertex to itself. If you look at the adjacency matrix, it means it's a 1 in the diagonal, right? So the diagonal of the matrix, you can read that very quickly. Are there any loops or not? You can read them very quickly from the diagonal. How do you know if a graph is undirected? It's a symmetric matrix, right? So answering your question, but you had answered that already by yourselves. So so if you look at the adjacency matrix, you know that you have an undirected graph exactly when the matrix is symmetric, right? So its transpose is equal to itself. Little aside, a multigraph. Remember, I said we're not going to deal in exercise or anything like that with multigraphs. What's a multigraph? You allow several edges between two vertices. How can you encode multigraphs? You can probably guess that, how you would do that, right? So if you have, let's say, 5 edges between two vertices, then you would put a 5 in that entry in the matrix, right? So multigraphs correspond to matrices with positive integer entries. Okay, but again, I'm just mentioning that briefly. We're not going to go there. Okay. All right. There is another matrix which is it's similar flavor. It's usually a much bigger matrix, which is called the incidence matrix. And rather than connect vertices to vertices, it connects vertices to edges. Okay, so it won't be a square matrix in general. Okay, and it also, if there's, in fact, there is a whole field of graph theory called algebraic graph theory that plays with these matrices and their properties. And there's like tons of stuffs happening with these where you look at eigenvalues of the matrices and this and that. There's like lots of magic, lots of stuff, which I don't know that much about. That's a bit far from what I do. But there's like dozens of books on this topic. So if you have an undirected graph G, okay, with vertices V and edges E, now you need to choose an ordering of the vertices, let's say V1 to Vn, and also an ordering of the edges E1 to Em. Okay, so the incidence matrix, remember we say that an edge is incident to a vertex when that edge is, defined using that vertex. So the incidence matrix of G is the n by m matrix where Mij, so the entry at row I, column J, is 1 if the edge E index J is incident to that vertex Vi, right? So you have vertices and edges, and you put a 1 if that edge is incident to that vertex, and 0 otherwise. Okay, so it's the same principle. It's not more complicated. Usually this matrix will be bigger because you'll have a lot of edges, let's say. So here's an example. It's my same graph, okay? But this time I'm going to look at the incidence matrix. So the rows correspond to my vertices. I've ordered them the usual way, A, B, C, D, E. But now the columns correspond to edges. So I've chosen an ordering of the edges. I call them E1, E2, E3, E4, E5, E6, right? You're going to get a different matrix if you choose a different ordering. But here, this is the ordering I chose. And you put a 1 if you have incidence between the edge and the vertex in question. So here, for example, this top one here, means that edge E1 is incident to A, which it is, right? Notice, and that should be fairly clear, look at the columns. How many ones are there in each column? There are 2 ones, right? Because that corresponds to an edge, and it is incident, unless it's a loop, it's incident to 2 vertices exactly, right? So for example, E3 is incident to A and E. So let's take a look, A, E, right? So, okay. Again, there's a lot of stuff that can be done with the incidence matrix by multiplying and adding and doing polynomials of matrices, and all sorts of magic happens. We're not going to go there. But you also see that this is a nice way to input a graph. If you have to program anything about a digraph or graph, you have a way of inputting the digraph or graph in the machine. That's one possible way of doing it. Okay. Okay, let's move on to graph isomorphism. So here are 2 graphs. The graph on the left has vertices 0, 1, 2, 3, and it's a cycle. It's a 4 cycle. And the graph on the right has vertices A, B, X, and H. But you see it's also a 4 cycle, right? It's just drawn in a different way. And when I use different, stupid iMac mouse. So it has different names for its vertices, but basically it's the same graph, right? It's just, we just renamed everything and we drew it differently, but it's the same graph, right? Talking about one or the other is the same. So we say that these graphs are isomorphic. That's the terminology. Okay, so let's define this properly. So what does it mean that we're renaming things? Is that we have a bijection between the set of vertices, but a specific kind of bijection. So I have 2 graphs, G1 with vertex set V1 and edge set E1. And I have a second graph, G2 with vertex set V2 and edge set E2. Now we'll say that they are isomorphic. This is the notation right here. So what does it mean? It means that there is a bijection, let's say F, which is what we call an isomorphism. It's a bijection from V1 onto V2. So again, it means that it is 1-to-1 and onto. So it's a pairing between V1 and V2, but not just any pairing. It has to preserve the edge structures. So it means that whenever UV is an edge in the graph G1, then if I apply the function f of u, f of v is an edge of E2. Okay, so it sends edges to edges. You can't break them. So let me show you an example, because this is sort of a mouthful. I mean, if you read this, it's very technical. In the end, this is very, very natural. Okay. So what do we mean by an isomorphism? Why do I say that these 2 graphs are the same? Because I'm saying, well, this is a 4 cycle. If I start here at 0 and I follow the cycle, I come back, I got my 4 cycle. And here I do the same, right? I start at A and I go A, B, X, H, A. Not A, B, H, X, A. That doesn't work, right? I have to follow the edges in following the cycle to notice that this is the same graph, okay? So what I mean now by an isomorphism is a map that tells me that these are the same. So 0, I would send to 8. I mean, there are many, many possibilities here, okay? Because this graph has a lot of internal symmetries. There are many possibilities of isomorphisms between these 2. But let's say that I choose that 0 goes to A, right? Then I chose here that 1 goes to H. But you see, I have an edge here between 0 and 1, which means that their image, there must be an edge. So A to H, right? 2, I sent to X. Now I have to go to X. There's no choice, right? Because I'm following 0, 1, 2, 3. So A, H, X, and F of 3 is B. X goes to B like this, and I've got my isomorphism, okay? Does that make sense? It's a bit more abstract, but the principle is sort of straightforward, I think, if you think about it a little bit. Does that make sense?
Yep.
All right. Okay. Now, let's say that we play this game, and you will play it in the exercise, obviously, but you will play it with small, and in the WebWorks also. You are going to play with this game with very small graphs. If you have graphs with 1 million vertices, this becomes very difficult. But let's say I give you 2 graphs and I tell you, I ask you, are they isomorphic or not? Okay. For sure, they need to have the same number of vertices, right? But if you start, let's say you want to brute force this, you say, okay, I'm going to, let's say I have 1 million vertices here, I've got 1 million here. Let's look at all the possible bijections between these two. Well, that would be 1 million factorial, which is going to blow up all the computers in the universe at the same time. So that's not good. Okay. So brute force is really not a good way to do this. Okay. Now you might check some necessary things. For example, you might count the number of edges on both sides. You might check that they are both bipartite, that they have the same degree sequence and things like that. It's possible to check these things, but it turns out that you might check a lot of these things which are easy to check and still have graphs which are not isomorphic. And I'll get back to that because it's a very, very important research question, which is still very, very much alive right now. And I'll just mention this in just a sec, okay? But let's look at an example. So this is a small example. I have 2 graphs, G and H, and I'm asked, are they isomorphic? Now, these are small enough that you can sort of mess around with them and figure it out. Now, if you are good visually, you might see, okay, if I take, let's say these 2 edges here, right? I've got like a rectangle and a path of length 3 joining the 2 opposite vertices here. Do I have something similar here? Yeah, actually, if you look at this part, if you were to take it outside here and put this inside, you'd see the same picture, right? So once you've visualized this, then you can just write down where each vertex is supposed to go, right? So let's take a look. Yes. So these graphs are indeed isomorphic. So I said, okay, U1 will be V6, right? And U2 will be sent to V3, and then U3 to V4, and U4 to V5, right? And then U5 would be going to V1, yes, and U6 would be going to V2, which is what I was describing, right? So this is my outside rectangle, and this is the diagonal of length 3 connecting these two, okay? But we'd have to check. So this is clearly bijection. I mean, that's the easy part. But then you have to check that whenever you have an edge on this side, this map sends it to an edge on the other side. Okay, so then you would check. But hopefully you can visualize what's going on. You can see, otherwise then you have to check edge by edge that everything is preserved. Okay, so that's your isomorphism. Okay. Yeah, so there's a connection to the adjacency matrix and to that ordering of the vertices I talked about. Okay. Now, if you look at graphs which are isomorphic, it's the same as saying that there's a way to order the vertices of both such that the adjacency matrices are exactly the same. That's an equivalent definition of isomorphic graphs. Okay, so if I use the ordering U1, U2, U3, U4, U5, U6 for G, and then I look at my isomorphism, right? And that would tell me, well, order then the vertices of H as V6, V3, V4, V5, V1, V2, and look at the adjacency matrix for that particular ordering, you will get the same adjacency matrix as this one. So the problem might be seen as follows. So I give you two graphs. I say, can you find an ordering of the vertices of both that will give you the same adjacency matrix? So is it possible to do this efficiently? Okay, so that would be my question. Nobody knows if it can be done efficiently, although recent results, last 3-4 years, seem to point towards a positive solution, that there would be a polynomial time algorithm to do, but it's very, very, very tricky, very sophisticated. But this is graph isomorphism is one of those very rare natural problems that is not known to be polytime solvable, like easy. And on the other hand, is not one of those hardest problems, NP-complete problems. So it's like, it would appear to be some sort of intermediate problems. And people who do quantum computing, they're really happy when they have problems like that, because they think, we'll be able to use quantum computing to make it easy. But it might not be easy for normal computers, right? But it appears there's some evidence now that this might be a polytime solvable problem. But I can tell you, this is highly, highly not obvious. It is really a hard problem. It requires a lot of very deep algebra, group theory. Anyway, so that's a little aside. I think I am ready to move on to section 10.4. Are there any questions at this point? No? Okay. So 10.4, connectivity. Some of this stuff is easier and some of this stuff is not as easy. Anyway, we'll see. But I mean, again, it's mostly I'm going to show you one theorem if I get there, but it's mostly just basic definitions. And it might look more complicated than it actually is, because we have to write it out formally, but the concepts are very simple. Okay. So informally, what is graph connectivity? So if I give you a digraph or a graph, you want to know if you can go from one vertex to another following edges, right? Which I mean, if you have, let's say, a network, and you model it as a digraph saying, these two machines, this machine can send a message to this machine, you might want to know if that very far away machine can send a message to that very far away machine there. So you have to know, is there a path of edges, directed edges from that vertex to that other vertex? Or maybe it's flights from one city to another. So that's the intuition behind this. It's a very simple, natural concept, okay? So to define this, I need to define what a path is. And that looks scary when you see the slide like that, but it's not, okay? It's just, if I have a graph and I have two vertices, U and V, in the graph, I want to define what a path is from U to V. So what is it? It's basically, you start at U, and you use an edge to go to another vertex, and then you use an edge to go another vertex, and you keep on going until you reach V, right? That's the idea. So I need to write this down, okay? So a path of length N is a sequence of N edges, E1 to En, okay? But if I just say that, then that's not really what I want. I want these edges to be one after another, so they have to share vertices. Just like if you look at the picture at the bottom, it tells you exactly what you want. So you want to start at U, right? Then use edge E1 to get to a new vertex, let's say X1, and then use an edge E2 to get another vertex X2, keep on going until you reach the vertex V. Okay, so your n edges are as follows. You have to find vertices. You can see the path as a bunch of vertices or as a bunch of edges, either way. Okay, so you have vertices x0 to xn, where x0, where you start, is u, xn is where you end, it's v, and xi plus 1 is an edge each time. Okay. Now notice that I don't make any conditions here on whether these edges are different or the vertices are different. You might have lots of repeats. It makes no difference. Okay, so we don't disallow situations where the vertices or edges are not distinct. So here's an example. Rather than list edges, I've just listed the vertices one after another. It's easier. It just takes less space. So I've used that graph again because, well, I'm lazy. And so it does the job, right? So here is a path of length 6 from B to D. So it's B, A, E, C, E, C, D. Notice that I'm going through the same vertices several times. It has length 6, right? So I started B, A, E, C, back to E, back to C, and then D. Yep, right, 6. So 1, 2, 3, 4, 5, 6. So it's a path of length 6. I've used the same edge twice, right? Actually more than once, but in that direction, I've used it twice. And I've used the same vertices several times, right? BAED and BACD are different paths of length 3 from B to D. Okay. Now, if no edge is repeated, we call the path a simple path. A walk is also used. Okay. And if you start and end at the same vertex, if U equals to V, we call the path a circuit. Okay. So here's an example: A, E, C, D, E, C, A. A, E, C, D, E, C, A. Yeah, so that's a circuit. Okay, so the concept, I think, is really straightforward, very simple. If you have a digraph, it is exactly the same definition, right? Except that you have to traverse the arcs in the right direction. You can't go backwards, okay? So, but if you look at the definition, everything matches. But I mean, intuitively, I can't go from V4 to V3 here. That's not allowed, okay? So here's one: V1, V1, V2, V3, V2, V3, V4. This is a path of length 6 from V1 to V4. Notice that I looped in V1 here, right? That's 1, 2, 3, 4, 5, 6, okay? And again, if you start an N in the same place, you call that a circuit, okay? Just a name. All right. So the length is just the number of edges, arcs that you're using. Okay, connected graphs. So what does it mean for a graph to be connected? Like the name implies, it seems to imply was chosen for that reason, is you can go from any vertex to any other vertex by some path, right? So an undirected graph is connected if for every pair of vertices U and V, there is a path from U to V of any length, it doesn't matter. So the graph G here is clearly connected, and the graph H here is clearly not connected. If I take a vertex on this side, I cannot find a path to a vertex on that side, okay? Now, here's a little aside again. If I show you a picture of a graph, right, you'll see, unless it's drawn in a very stupid way, you will see immediately if it's connected or not. But if I just give you a long list of edges, right, let's say there are 1 billion edges that I just list like that, and I ask you, is this thing connected? I mean, it's not too hard to see that you can do this efficiently, but for a long time, it was not known whether you could do this um, using very little memory space. And it was proved less than 20 years ago by a student, Omer Reingold, that you can actually do it. This is not an easy proof. This is very tough. So you can use a logarithmic amount of space to check connectivity. So if I give you two vertices in a graph, just checking that, you can use a very, very limited amount of space to do this. This was really hard. It's a non-trivial result. But anyway, that's for the fancy people. I'm losing customers by the minute. Yeah, okay. So the next definition, I need the notion of subgraph and induced subgraph to define the notion of connected component, which is strange. But anyway, so this definition actually comes from 10.2. I skipped it in 10.2, but here it is. Again, it looks more complicated than it actually is, although the distinction between subgraph and induced subgraph is a bit, you have to be careful with this. Okay, so let's try to define this properly. I have two graphs, G and H. Okay, G has vertex set V, edge set E, and H has vertex set V prime and edge set E prime. I want to define the notion of subgraph, to say that H is a subgraph of G. So this is the more relaxed definition. So I say that H is a subgraph of G if the vertices of H are vertices of G and the edges of H are edges of G. Okay, so that's what a subgraph is. I'm going to show you a whole bunch of examples on the next slide. Okay, now induced subgraph is a bit different. So an induced subgraph is a subgraph, but I ask for something more. I ask that if two vertices are in the subgraph and there was an edge between them in the big graph, it still has to be there. I'm not allowed to erase any of the edges, okay? So another way of seeing this is to say, okay, I have this big graph G. I choose some vertices in G, and I erase all the edges that are not relevant to these vertices, but I keep those which are relevant, okay? So that's what you call an induced subgraph. So this is the subgraph induced by the vertices that you chose, okay? So let me illustrate this, because it's not, again, it's not a complicated thing, but you just have to be very careful about this. Okay, so G here will be my, if you want, my big graph. Okay, now I have four other graphs here, H, K, L, and M, and I want to determine whether they are subgraphs of G, induced subgraphs of G. Okay, let's start with K, which is the easiest one of the bunch. Okay, K is not, it's not even a subgraph of G. Why? Because of the edge 0, 3. This is not good because 0, 3 is not an edge of G, so that's bad. Okay, so K is not a subgraph. To get a subgraph of G, what I need to do is just basically remove stuff. I can't add anything, okay? So let's take a look at H. H is a subgraph of G. That's easy, right? So the three vertices 0, 1, 2 are there, and I've got the edge 1, 2. Oh, that should be, yeah, no, that's okay. I just drew it in a weird way. It's confusing, but it is a subgraph. Confusing, but maybe it's a better exercise. So 1, 2 is an edge in G, so that's fine. So H is a subgraph of G. What about L? Yes, that's a subgraph of G. 1, 2, 3, all the edges are here. That's good. What about M? 1, 2, 2, 3. Yes, that's a subgraph. Okay, so all of these three are subgraphs. K is not, it's bad. It has the edge 0, 3, which is not in G, so that's gone. Now, of H, L, and M, are there any which are induced subgraphs? Okay, well, so how does it work? What you have to do is to see that you haven't erased any edges, okay, other than those which are incident to vertices that you remove, okay? So let's take a look at H. H is not an induced subgraph because 0, 1 is an edge in G, so it should be here, okay? So in other words, how do you get the induced subgraph that should correspond to H? You look at 0, 1, 2, 0, 1, 2, it should be that triangle there. Okay, so 0, 1 and 0, 2 are missing. That's no good. Okay, what about L? Yes, L is good. 1, 2, 3, all the edges are there. Everything is good. And M, you see, is not induced because 1, 3 is missing. Okay, this might take a little bit more work on your part by yourselves. That's possible. Okay, but it's just terminology. It's just what's hard at this point is it's not clear probably for you guys if you've never seen this before. Why should we define this? Why do we need this? So by playing with these things, at some point you'll say, oh yeah, okay, I see why we might want to this notion of subgraph and induced subgraph. I have to say that no, scratch that. But I mean, for me, induced subgraph is the more natural concept. But that's personal, I guess. Anyway, okay. So what's a connected component? Now I can define what a connected component is. Again, this is a very natural, simple concept. But to define it properly, I needed the notion of induced subgraph. Okay, so here's, before I go into the definition, here's a picture of a graph. So this whole thing is a graph. Okay, so what are its connected components? It's the islands of connectivity. So you can see from the picture exactly what the connected components are. This is a connected component. This is a connected component. This one, and this one. Right? So it's those connected pieces. But now I want to define this properly. And if you try, you'll see that any way you try to define this, it'll just get slightly messy. So this is one of the less messier ways of doing this. So if I have a graph, what a connected component of G is an induced connected subgraph, which is maximal. Okay, so so for example, so why this maximality condition? If I take just the edge, which is here, that's not a connected component, right? It's not big enough. I have to include, I have to include everything that is connected, okay, to that piece. So it's an induced subgraph, which is connected. It's a connected component. It should be connected, but it's as big as possible. Okay, so that's what a connected component is. Another way you could define it, but it'll get messy, but in different ways. Say, okay, take a vertex and look at everything you can reach from this vertex using paths, right? What you will get is a connected component, and repeat for all other possible vertices. That's another way of doing this. I could have also tried to do it using an equivalence relation, but we didn't see those when we saw relations, so that didn't help. So anyway, okay.
In the last slide, is G the whole graph?
You mean in the picture here?
Yes.
Yes. That's the hard thing about these pictures. So in my example here, this whole thing is one single graph.
Okay.
Yeah, and these are its connected components. Yeah. Yes. Okay. Now, if you have a directed graph, so you can go in more detail in a sense, because now if you can go from U to V, if there's a path from U to V, it's a directed path, right? So you might ask for a component to be connected from any U to any V in that component, you'd have a path. But what does that mean? It means in particular that if you go from a certain U to a V, you have to be able to come back from that V back to U, right? So this is different than just that the picture is connected, right? Without looking at the orientation. It's a bit more sophisticated. So here is an example of what I'm trying with great difficulty to say without going into details, is if you look at this digraph as a graph, if you just forget about the orientation, it's connected, right? So you can always walk, if you're allowed to walk against, let's think of these as one ways, but you're walking around. So you can walk in the one ways, but you can walk in the wrong direction, right? So it's connected, right? You can go anywhere you want from anywhere you want. But if you're driving around, you see that if you start, let's say here, you can drive to this place, but you'll never be able to come back. Once you've reached this point, you're stuck, right? There's only one way is the wrong way. So we want to be able to make a distinction between these situations. Okay, I've lost another person. My God. So a directed graph will say is strongly connected if for every pair of vertices, there is a path from A to B. So notice that, again, I'm saying for every pair, so you have to be able always to go back and forth, okay? So here, this digraph is not strongly connected, because if I start with the vertex here at the bottom right, I'll never be able to go to the other vertices. I'm stuck there. Okay, but it is weakly connected. So we'll say it's weakly connected because if you erase the orientations, you get a undirected graph, and it is connected. Okay, so there's a distinction here. So here's an example, okay, of a digraph, and I want to, so I've defined the notion of strongly connected. Now I want to define the notion of strongly connected component. You can guess what this is, or a strong component of a digraph. So these are the pieces, the biggest pieces, which are strongly connected. Okay, so formally, I have to define this as an induced, strongly connected subgraph, which is maximal with this property. So I can't make it any bigger, okay? Now, this is a bit trickier. I mean, just looking at the picture, you actually have to think about it to see where the strong components are. I don't know if anybody can see where they are.
This one from 4, 5, and 6.
Yeah, that's a strong component for sure. And that's the other one here. 0, 1, 2, 3 is one component, strong component, and 4, 5, 6 is the other. Yes. And how do I see this? Okay. So look at 0, 1, 2, 3. You see that there is a cycle, directed cycle going through 0, 1, 2, 3. So once you have that, you know that they must be in the same strong component, right? You can go from anyone to anybody else. But now, and the same is true for 4, 5, 6. You have this directed cycle connecting all of them. But look at the arcs in between the two pieces. They all go in one direction. So once you leave 0, 1, 2, 3 to go into 4, 5, 6, you can never come back. Okay, so there are two strong components of this digraph, 0, 1, 2, 3, 4, 5, 6. Yeah. All right, so these are a bit trickier to spot. You have to work a little bit more than just if it's the undirected case. Components are like super easy. When you have a picture, it's really easy to see. Okay. I think Let me see. Yeah. I'm almost done. Okay, this one. Okay. That's the theorem I was talking to you. Yeah, telling you about. I'm going to switch to the whiteboard in just a sec to try to argue this proof, because just the way it's written like that it's just really difficult to understand the proof, but it's not really that hard. Okay, so so here's the theorem. Here's the statement of the theorem is that, so I'm going back to adjacency matrices, and I want to talk about the connection to adjacency matrices to paths. Okay. So if I have a graph G, okay, and it has adjacency matrix A, let's say the vertices are ordered V1 to Vn. Okay. I want to compute the number of paths of length R from one vertex to another. Now that's can be pretty tricky, right? But it turns out that there's a connection to matrix powers, which is really cool, okay? Which is take the adjacency matrix, compute its rth power. So that's the length you want, let's say path of length 5, you're going to compute a power 5, okay? And you want to know how many paths of length 5 there are from Vi to Vj. Look at the entry Vi, Vj, and that's the number of paths that you're looking for. Okay, so I'm going to do the proof on the whiteboard in just a sec. Okay, because just written like that, it's not gonna. It's pretty tough to figure out. But before I move on, let's just go and show you an example here. Okay, so this is my graph G. Okay, and I've chosen the natural order for the vertices 1, 2, 3, 4. Okay, so this is the adjacency matrix for that graph. Okay, and I computed its third power. So it turns out this graph has very nice structure. So the adjacency matrix has very nice structure, and so it turns out that the powers of this matrix are easy to compute. Yeah, it looks like but anyway, you can do it by yourselves, but it's easy to compute. So what this means is that if I'm looking for paths of length 3, then the number of paths of length 3 between any two vertices is given by this matrix. So let's say I want the number of paths of length 3 between 1 and 2. Okay, I'm going to look at the entry 1, 2. It's this here. So this tells me that there are 4 paths of length 3 between 1 and 2. So is that true? Let's see. 1, 2, 3. 1, 2, 3. 1, 2, 3. How many do I have now? Okay, that was 1, 2, 3. Shouldn't I have, where's the other one? Okay, I've got 1, 2, 1, 2, then 1, 2, 4, 2, 1, 1, 3, 4, 2, and 1, 3, 1, 2. So there are 4. Yes, there are exactly 4 paths of length 3 from 1 to 2. That's what the matrix tells me. And I've verified this for that particular graph. Okay, this is a very small graph, okay? But this is a very cute little observation. So I'm going to show you the proof in a sec. And one last slide before I do that. I've added this slide here because if you're trying to do the WebWorks, you will see that it talks about trees. So what is a tree? A tree is a simple graph which is acyclic and connected. What is acyclic? It does not contain an induced subgraph, which is a cycle. So it has no, there's no circuits in the graph as defined in these slides. There's no induced cycle in the graph. Okay, so a tree, and I'll show you on the whiteboard just a sec why it's called a tree. You'll see why. and a bunch of trees is a forest. Aren't mathematicians smart? So let me show you. So you might need this for the okay, I want to prove this theorem. Okay, so just before I do so trees. So what's a tree? A 1 vertex tree, a 2 vertex tree, a 3 vertex tree, 4, and so on. That's what a tree is. You might have seen these if you've done some. Right? So you see why they're called trees. These are trees. Okay, they have to be connected. If you have something that looks like a tree, but you have different pieces, it's a forest. It's a bunch of trees. Okay, so these are trees. No, so they're acyclic. They don't contain cycles. Trees are absolutely wonderful graphs. There are so many nice things about them, and we'll get to see a few of them soon. Okay, the theorem. I'm not going to write down a formal proof because it's in the slides, but I'm just going to try to explain why it's true, and you'll see it's not super tough. Okay, so I have a graph G, and I have A, its adjacency matrix. Remember what this is. The entry ij is 1 if vi is adjacent to vj and 0 otherwise. Okay, so that's the adjacency matrix, and we want to prove the theorem is, let's say, a little aside here, is that the entry, sorry, the ijth entry of a to the what did I use? I used power r. I'm going to use the same indexing of AR is the number of paths of length r from VI to VJ. Okay, I'd like to try to convince you of this. Okay, first of all, observe. That's an easy observation. This is clearly true if r equals to 1. Right? The adjacency matrix has a 1 in entry ij if there's an edge between vi and vj. What's a path of length 1? It's an edge. So this is just, there's nothing to prove if r equals to 1. Hopefully everybody's okay with this. Yes?
Yep.
Yeah. Okay. So this looks like a job for induction. Okay. On R. Okay. So we've got it for r equals to 1. We're going to assume it's true for a fixed value of r and show it for the next. Okay, so here's how it goes. Okay, so true for r equals to 1. That's done. Now, suppose true for some fixed r greater or equal to 1. Show it's true for r plus 1. Okay, so what does that mean? It means, so our hypothesis is that the entry ij of a to the r is the number of paths of length r vi to vj. Okay, so this is what I assume this is true. And I want to show that essentially the same thing holds for the next power, a power r plus 1. To show is the ijth entry of a power r plus 1 is the number of paths of length r plus 1 from vi to vj. This is what I want to show. Okay. So basically what you want to see now, so how do you get AR, how do you involve the induction hypothesis? Well, AR plus 1 is a power r times a, right? So a to the r plus 1 is a power r times a. That's the key, right? So how do you multiply matrices? These are all square matrices. You can multiply, obviously, everything is nicely defined. So what is a power r times a? Row times column, right? So let's say that I want the ijth entry of this matrix. I entirely understand if at this point you are staring at your screen and going, what the hell is going on? It's okay, right? I know this is like a little heavier, especially since I dulled your brain with all sorts of really basic definitions on graphs, and I was suddenly, so what's the ijth entry of this matrix? It's row I times column j, right? So it's row I of a power r times column j of a. Okay. And what is that? Okay, so let's just take a picture. Let's look at a picture. I've got VI, right? And I've got V1, V2, right up to Vn. And I'm looking at the entries here. My induction hypothesis is that all these entries are the number of paths of length r from Vi to all of these guys. Okay, so this is number of paths length r, Vi to V1, V2, right up to Vn. Is that okay?
Yep.
Where does what did happen to the VI?
Sorry?
I'm just not sure what the VI.
Okay, because I'm looking at row I of the, yeah, I mean, it's just okay, so let's do that. I have the matrix like that, and I'm looking at Vi, Vj. So in A, this entry is either 1 or 0, depending on if there's an edge or not. But in A, Yeah, let's call it, actually, you know, let's not call it VJ, let's call it VK. So this will be the number of, let's call them R paths. It's just easier. VI to VK. This is matrix AR. Is that okay?
Right, yeah.
Okay, so that's what I'm looking at row I of this matrix. So each entry is just the number of paths from VI to V1, VI to V2, right up to Vn. We've chosen VI. I mean, I is just some fixed index. Yeah. Okay. All right. So now I'm multiplying this by column J of A. So this is the column corresponding to VJ. And what are these numbers? They're zeros or ones, depending on whether there's an edge. So this is 0 or 1. If no edge, VK, V1, Vn to Vj, right? So depending on whether there is an edge, V1, Vj will be 1 if there's an edge and 0 if not, right? All of these. Yes? I know this is heavy. Okay, well, so I'm multiplying this row. I mean, if anybody has a question, just jump in, because you probably will be asking a whole bunch of people's question at the same time, and I can answer it. Just interrupt me anytime. So I'm multiplying this row times this column. So what does it mean? Okay, what I'm hoping to get the number of paths of length R plus 1 from VI to VJ. So what's the connection? Let's see the connection. I've got so in G, I've got VI, I've got VJ, and I want to look at paths of length R plus 1. From VI to VJ. I've got information about paths of length R from VI to anything, and paths of length 1 from anything to VJ. So how should I visualize a path of length R plus 1 from VI to VJ? I should visualize it as follows. I have a path of length R to some VK, which is adjacent to VJ. That's what a path of length R plus 1 is, right? You walk along R edges until you reach some vertex, and then you finish at VJ. Yes?
Yes.
Okay,
Yes.
yeah.
Yeah. So imagine that I have 12 ways of going from VI to VK. That means of length R. So it means if I have 12 ways of doing that, then I have 12 paths from VI to VJ of length R plus 1 that go through that particular VK, right? So let's write that. So the number of R plus 1 paths VI to VJ through VK is equal to the number of R paths VI to VK. That if you understand this, the rest is, I mean, that's the key. That's the key idea. Okay. So if I want to count the number of ways of going from VI to VJ in R+1 edges, I count the number of ways, let's say, going from VI to VK, R with R edges, right? And then I do that for every possible VK, which is adjacent to VJ. So I multiply by this number by 1 if the vertex is adjacent to VJ, and by 0 if it's not adjacent. Okay, so well, let's put some values in there. So let's say my column is 5, 0, 2, 3, 1, 1, 6. So this would be the number of R paths from VI to V1, V2, V3, V4, V5, V6. Okay, and here we'd have, let's say 1, 0, 0, 1. Let's do one less, so I can fit the whole thing. Right, so like this. So when I'm multiplying, I'm gonna get 5 times 1 plus 0 times 0 plus 2 times 0 plus 3 times 1 plus 1 times 1 plus 6 times 1. Okay, so this is the number of paths going through V1. So this is, let's say, VI going to V1 adjacent to VJ. Here, there's nothing. Here would be the number of paths going through V3, but V3 is not adjacent to VJ. Okay, so, and this one would be VI to V4 adjacent to VJ. I'm not being very formal, but I'm just trying to convey the idea that maybe I'm not doing this very well. Yes, no, maybe.
I think it works.
Yeah.
Yeah, that's fine.
Okay. So, but that's really the key idea right here. This is the trick. Okay, so I'm trying to count the number of paths of length R+1 from one vertex to another. So I look at all the paths of length R to any possible vertex, and then from all these, one shot to the other one. So if you look at the product of the row and the column, that's exactly what it encodes, which is, I mean, it's sort of magic, right? You're counting paths in a graph, and it turns out that if you take a matrix product, you get the numbers that you're interested in, which is pretty cool. So yeah, so that's my attempt at clarifying this in the very weird state that I am today. So I'll stop here. Let's say sorry. So spend a little time with it by yourselves and then come back with some questions. Okay, I'll stop here, especially since it's time to stop. Unless there are questions, if you have questions, comments. Yes, no, maybe.